Hi everyone, and welcome to Boson Protocol's latest webinar. We're here to discuss the latest collaboration between me, Justin Banon, and Professor Jason Potts. Jason and I, not so long ago, or back in November 2022, collaborated on an article which was published in the World Economic Forum, which explained how Web3's programmable commerce layer will transform the global economy. And we've recently collaborated again, really to extend that thinking on a paper which is called Digital Institutions Create Wealth by Increasing Economic Complexity. Or in other words, how Web3 can enable a computable economy and sort of exponential wealth. So firstly, welcome, Jason. Perhaps you can introduce yourself to everyone.
Yeah, thank you, Justin. It's great to be here. Well, hello, everyone. So I'm Jason Potts. I'm an economics professor at RMIT University in Melbourne, Australia. I'm the founder and director of the Blockchain Innovation Hub, which was one of the first blockchain research centers set up in the world back in 2017. And excited to work on this project. And I was just reflecting, I like the second version of the title better than the one that we've actually given it. It's a long descriptive title, but the idea of just increasing computational complexity creates wealth is, I think, what this paper is really about.
Brilliant, yeah. And so perhaps we could start. If I explain what we're going to do today is we're going to try and break down section by section this quite dense academic paper and try and decode that for everyone, because I think it makes some really important kind of claims for what crypto real world assets can enable from a sort of an economic perspective, but also some important implications for humanity and society as a whole. So perhaps I could start with Jason, asking you to kind of give your overall sort of description of what the paper is about.
Yeah, let me have a go at that. So the paper is it's an economic argument. And it's a very classical economic argument trying to answer the question, where does wealth come from? Why are some countries rich and some countries poor? It's the question that economists have asked since the beginning of economics. And the answer that we give here is fundamentally trying to express this in terms of information or in terms of computation. And we distinguish between the importance of the growth of knowledge, the growth of institutions and the development of institutions, and the way in which the way in which the evolution of institutions enables more complex knowledge and more complex coordination, and that's the source that's fundamentally the origin of wealth. And what's interesting about this argument, why it's novel, is it locates that source, the main driver of long-run economic growth and development, in the computational layer of institutions, not in resources, not in human capital, not in industrial technologies, but in coordination technologies and institutional technologies. And that's the connection then to, if we can have all of the parts of an economy able to coordinate and exchange information and compute with all other parts of it, we can get these step changes in the use of knowledge and the growth of knowledge and all of the things that enable an economy to produce wealth. And our argument is that we're right at a transition right now. For hundreds of years, we've had the Industrial Revolution working its way through with industrial technologies. And we're right at the beginning of a new institutional revolution. And I think that the role of sort of Web3 technologies, sort of digital technologies, in driving that that's the claim that we're making, is that this is a moment of transition in the long run history of the global economy, and we're trying to sort of elaborate and describe that up describe what's driving that in this paper. That's my short version. It wasn't short at all.
But I think that's the pretty comprehensive summary. I mean, I'll have a stab as well, and I mean, the way I view this is that crypto is an upgrade, is an evolution, not to the sort of things that that can be built within the economy, but to the underlying kind of computational substrate of the economy itself. So in a similar way that if you look at life has gone from sort of, RNA, which supported viruses, to DNA, which supports this huge diversity and complexity of life, that this blockchain substrate supports much, is more reliable and deterministic compute, and on top of that you can then have far more complex economic applications running. And I think, as you mentioned, there's this clear link between economic complexity and wealth. And so that's the sort of I think the way I view it is this sort of substrate upgrade. And okay, so hopefully that's kind of whetted people's appetite and given them an understanding of some of the quite bold claims that we're making. Let's try and sort of break down that argument then. I mean, I'll start with the first one because it's quite simple, and then I can pass you some more complex ones. But there is a kind of claim in economics, and I mean, I sort of first exposed to this with the Complexity Economics book by Eric Beinhocker, which is The Origin of Wealth. But the claim is that the wealth within the economy is linked to the complexity and of the economy. So that's like the kind of first fundamental claim that we make, and you can see this sort of exponential increase in complexity in wealth. So like 100x increase in wealth per person over the last 250 years. But perhaps Jason, you can talk a bit about how wealth is generated, and in terms of industrial technologies and institutional technologies.
Yeah, sure. So I think the idea that economic growth isn't just a piling of stuff on top of stuff. It's not additive in the sense that the sort of model of investment-led growth suggests. Beinhocker's point was that economic growth is more like biological growth, that it's an increase in complexification. An economy that produces more wealth is more complex than an economy that is relatively poorer or less fecund. And that's a very old idea. That's Adam Smith. That's 1776. That's the beginnings of economics. Was this insight? Chapter 3, book 1, The Wealth of Nations. Adam Smith argued that the source of economic growth was specialization. What he meant was that the key resource in an economy was knowledge, was skilled, specialized knowledge. And what he asked was, what causes that knowledge to grow? And his answer was the extent of the market. And that was a surprising answer, because he linked this idea of institutional mechanisms, the market, to human specialization and skills, around the butcher and the baker and the tailor and so on, about how specific their skills were. And he says the larger the market, the more specific their skills. And why is that a significant claim? Because he said, and that's where wealth comes from. And what he meant was that the more specific those skills, the more that they can be combined in the other institutional technology, a factory, to create this incredibly complex industrial organization of production. And the market was determining how fine that was. So that's, if you've never studied economics, you don't need to now. That's economics right there with that claim. But what we're just recognizing is that what he's describing there is an increase in institutional complexity in the market, an institution, in the factory, an organization, and greater wealth drives that out. So that, that 250-year-old insight is still true, fundamentally still true. But the leap that we're making is to ask, all right, how does those technologies improve? Because there's two technologies in that story. There's the technologies of industrial production, the factory, whatever it's making, pins or cars or whatever. And then there's the technology of the institute, the market, and the factory itself. And most technological change is industrial technological change. It's the sort that you patent. That's the sort that when we think about changes in the chemical industry or the aircraft industry, or or pharmaceuticals, or just changes in things that are made by scientists in labs and then pushed into markets. But that's one sort of technology in an economy. The other sort is the technologies of coordination. That's soft technologies in a sense, harder to patent, harder to see, harder to change, because we do get enormous changes in those technologies. It just doesn't happen very often. So the development of the factory itself, the idea of the factory, and an institutional technology. The idea of a factory timetable, of everyone using the same clock to coordinate their activities, an institutional technology. Everyone using the same clock enables us to schedule things, that's railways, or the timetables and so on. So coordinated clocks, an institutional technology. Standards, an institutional technology. Marketplaces, which are based on standards and coordination, an institutional technology. We sort of, the main institutional technologies we have in the economy today are hundreds of years old. They don't change very often, and when they change, they produce massive shifts in coordination possibilities. So the argument that we're sort of building on here is that there are two fundamental types of technologies in an economy: industrial technologies and institutional technologies. Industrial technologies change thousands of times a day all over the world and just drive the frontier of production forward. Institutional technologies move forward in leaps. They just stay, not much changes for decades, hundreds of years, and then they leap forward because they're so hard to change. And the idea is that the digital computers, the digital revolution, which we're 60, 70 years deep into that now. Once they become ubiquitous enough, once you get them in everything, they enable a new type of institutional coordination of an economy, sort of a computable economy. And that idea of this massive leap in institutional technologies is that's the context in which we're talking about. And to Justin's point, if you look at those hockey stick curves, the whoosh, last time that changed, that was what we got. The institutional shift and then a grinding out of industrial technologies up the curve. We're right at the cusp of another one. And I think that's the story we're trying to tell here, is that this is a thing that is fundamentally good. It'll be fundamentally disruptive, but the thing about institutional technologies is that they don't change in part; they change the entire substrate of an economy, which means this is a challenging thing to do. So that's the sort of high-level view of what does technological change look like to an economist when we're looking at economies over hundreds of years or thousands of years. We don't see sort of railways and steam and petrochemicals and all these sort of things. We just see two big classes of technologies. One which changes all the time and a little bit, and one which changes hardly ever, but when it does, it changes a lot. And the transition we're at is of that second type.
Yeah, absolutely. So I mean, I sort of view it as almost like an operating system upgrade.
Yeah.
And the phrase institutional technology, perhaps is not that descriptive of the types of changes, but examples that we cite in the paper are, for example, written language enabling early societies, the constitutional reforms that created stable governments, and as Jason's mentioned, joint stock companies, universal time, standardized commodities and asset markets. And what we're saying about blockchains and Web3 technologies, they represent this, this upgrade of institutional technology that basically enables trust and coordination at scale. So we're talking about this increasing economic coordination, enabling all the elements to talk to each other at scale, at low cost, verifiably, and then reliably process the information inside of them. Yeah, okay.
So Justin, since you raised that, I think the interesting thing is to think of it as a language then, because when we think of language as something that is a spoken thing that has grammar and syntax and so on, but a language is just a general class of a structure or a medium that enables something to communicate with something else. And when it can do that, it can compute. And this idea of institutional technologies as sort of being a class of language, I think, is a really useful way of thinking about it.
Yeah, absolutely. And then, so given that this technology, blockchain technology, has this power, we then go on to sort of highlight the fact that for the impact of this technology to be actually economy-wide, rather than this new kind of computability being constrained just to on-chain transactions, then really what you need to do is to be able to bring all forms of capital, including off-chain real-world assets, into the economy with this same reliable and computable, what we call sort of hard tokenized properties as native on-chain assets. And we sort of talk a bit about how at the moment the economy, agreements and relationships and how the economy processes this capital is quite fuzzy, subject to default. It's mediated by things like contracts and courts, and whereas on-chain assets like DeFi, just have this very deterministic sort of absolute and reliable property. And if we can extend that to, if we can get the same trust assumptions that we have with on-chain transactions, and we can extend that to off-chain, then we unlock an economy-wide change.
I think that's that idea of an economy can only compute what it can see or what it can interact with. And the industrial economy that we've had for hundreds of years, the way all of the capital in that, the way all the parts of that compute through property rights, through the legal professions and the accounting professions and all of the other sort of business administration processes, backstopped by the courts, human, paper, all the way up. So it kind of works, and it's got reasonable coverage. Like in the beginning, it didn't have much coverage. There was maybe only land and a few types of capital, and gradually we've papered over more and more of the parts of the economy and strung them together with various professions and institutional systems. And it's incredible what we've built, but my God, it's slow. It's and incomplete. And the closer you are to it, the faster it works. So this is why some parts of finance are actually pretty efficient and fast, but other parts of the economy, the real estate markets, for instance, or education, credentialing and so on, are incredibly slow, incredibly expensive, incredibly lumpy. It computes, but it computes on a speed that you can barely even see it happening. So the idea of just taking something that's kind of working, but slow and expensive and a bit unreliable, and just making that better, making it faster, cheaper, more reliable, deeper coverage. That doing that process, but doing it over all the things in an economy. That's what we mean by this expansion of compute. And One, we think it's better because it's faster, it's cheaper, it's whatever, more reliable. But it's also, if it is faster, better, cheaper, we can do it to more things. So Adam Smith's point, the size of the market will increase, and both of those things feed back into increased complexity, driving wealth. So this is a good thing to do.
Yeah, absolutely. We then go on to talk about metasystem transitions, which is quite a mouthful, but essentially when we talk about sort of metasystem transitions, we're talking about, in complex systems, this sort of emergence of new levels of control or complexity. And so the example that I gave previously is that biology's sort of heredity mechanisms sort of evolved from proteins to RNA, then to the far more stable and accurately replicating DNA. And so as we've seen this sort of, again, this like upgrade of operating system, we see on top of DNA the sort of proliferation of a far more complex and diverse ecology of life than could be supported on, for example, RNA. And so, and again, we make this sort of point as the evolution of a language. And so, perhaps Jason, you can sort of talk us through, this sort of metasystem transition that we see the economy going through and evolving through.
Yeah, so I think if we start with this general idea of computation isn't just something that happens in computers, or as we're saying now, economies, but it's a general property of life, and this is an idea that it's been around for a while. Sort of the great John von Neumann sort of invented it back in the 1940s with this idea of self-replicating automata, but over the past many decades, physicists, biologists, computer scientists just have more and more start to conceptualize of the way in which we understand dynamics in the universe, the way in which we represent the universe in terms of computation, which means in terms of information, or this idea of a physical notion of information. And that's what's new about modern physics, for instance, compared to sort of, say, 19th century physics, where energy was real and there was no such thing as information. Modern physics is kind of, no, information is a real thing. And we see that, and what is meant by that is these computational substrates, that objects are thought of as results of computation, that laws of physics and sort of substrates in biological substrates are doing computation. An example of that is DNA is computation. It computes a protein, and it's a little bundle of information. So this idea of fundamentally the universe is made of information, and the substrates that hold that is not a radical idea. It's actually modern physics now. It hasn't sort of really come through. It's not sort of perhaps as widely understood, but that idea is what sits underneath this idea of okay, so what does changes in those compute substrates look like? Which is the idea of a metastable transition, or this idea of transition, that you have a particular type of substrate that enables a particular type of computation, and then the universe just unfolds exploring that. And in the process of exploring it, it'll discover new types of substrates, which kick, a new language, as it were, which then kick up a new type of computation and explores that. The name for those substrates is, physics, chemistry, biology, all the way, and at some point, economy, in which we get up. And these different levels, the physics, chemistry, biology, society, economy, they're all just different sort of layers of computation that are building on each other. They're not separate universes or realms. They're emergent. But so what we then have is this idea that we expect to see that the future will unfold, and dynamics and systems will either be exploring a space, exploring a substrate of what you can do with it, or in a process of transition between new ones, as new types of objects or substrates or languages open up new possibilities of compute. And that's a general sort of way of seeing the consilience, the unity of all knowledge and life, in terms of sort of emergent computation through these substrates. So very abstract way of describing everything we know about everything. But where that locates us is that's also true of the economy. The economy is a substrate where we're computing things, objects, capital, resources, all of the things that an economy is just a group of people and things coordinated to create value. Right? That's a coordination substrate to compute value. The limits of that are the amount of stuff that we've got, but also the technologies of what we can do with that. And where we started this conversation was with this idea that the fundamental limits on economic growth and wealth and prosperity are just as much around the coordination of what we can do in terms of having everything talk to everything else and discover value and communicate and exchange and so on, as with just recipes for producing new things, recipes for new types of steel or semiconductors or whatever. So this idea of a metastable transit, that we're in a sort of in a point of a metasystem transition, is something that is consistent with everything we know about life and the universe and everything. But it's an interesting idea that we might be right at the cusp of one right now in our economy.
Yeah, absolutely. And so then we get to the kind of point which I guess is absolutely core to Boson, really, which is, in order to enable this transition, we've got to get all forms of capital connected, and in the same way. It's at the moment the place we're at with the sort of diffusion of crypto technologies is very much on-chain transactions have these properties we've described, but when you look at tokenizing real-world assets, for example, the current state of the art in finance is to have trusted tokenization. So you're using blockchains to issue like a token, which is a sort of bearer asset, is a claim on a gold bar, for example, but it has exactly the same trust assumptions as issuing an IOU. Whereas if you had a claim on some cryptocurrency in a DeFi vault, you have got a much stronger sort of immutable claim. And where Boson and similar technologies comes in is building this sort of trust bridge, basically, so that if you have a claim on in the case of Boson currently, if you have a claim on a physical product, you've got an NFT that says, right, I can redeem this for this physical product. It gives you those same DeFi level assurances that either you'll get your product or the money back. And also extending this really importantly to finance real world assets, so that if you hold, let's say, an NFT as a claim on a piece of property, that you've got DeFi level assurance that either you'll get that property or you'll get your money back without having to go through recourse of the previous, the previous paradigm of, written contracts and courts, etc. And so, I think we're at this sort of juncture where connecting all of these off-chain assets is actually really crucial to enabling that complete meta-system transition at an economic level.
I like the idea of thinking of this as a Turing complete economy. That if everything can be if all of the off-chain assets can be wrapped and made computable, they can interact with everything else, and that that enables us to explore all of the possibilities that exist in that space. And that idea of a Turing complete economy is one where we can potentially unlock all of the value that's in there. And we don't have that at the moment. So we can unlock some of the value of capital, and this is again what global financial markets do for some types of capital, but there's a huge amount of value that's never unlocked. And thinking of that as computation, what that means is that the current sort of industrial economies we have are not Turing complete. There's value in there that we can't compute. The barrier to this is we need to bring those assets in, and that sort of that metaphor of what does it mean to improve for a computer to be better is what this idea of Turing completeness refers to. What does an improvement technically, structurally look like? And we have the same logic in an economy, that if we think of an economy as a digital economy is a new type of computer. And what type of computer is it, and how good is it? And what does improvement look like? What does it mean to make it better? And I think this fundamental insight that if we're right about all of that, then wrapping all the assets to bring them in is how we make this computer work better.
Yeah. I mean, that is a great way of thinking about it. So a Turing complete computer is a computer that can compute any computable program, and a Turing complete economy is an economy that can compute any asset or resource. There are none excluded. It can find
all of the value that's in there.
Yeah.
And that's an origin of wealth story.
Yeah. So okay, let's say we go through this transition and we get to a computable economy, and I think the claim we're making is that's similar to going from agrarian and to feudal to industrial. I mean, these great leaps, if you think about just human society as a whole and the levels of prosperity or poverty going to prosperity through these great leaps, and disease, poverty, life expectancy, all these huge kind of changes at a society level. What do we think are the benefits of a computable economy? What could this potentially unlock?
Yeah, so I'm a deep optimist on this, and I think this comes from it's easy to sort of be pessimistic in the short run about jobs and all the disruption in the economy, but if you pull back and look at this from a long time scale, as you just did then, wow, we've come a long way, and not just in terms of quality of life, but in just the amount of life. Our economies are bigger and better compared to how they were before. So the question is, what comes next? What comes after this? So I don't think of this as the end of history, post-capitalism, that this is as good as it ever gets. I think we keep moving up, and what happens next is that economies get even bigger, not because of growth in a very crude sense of just more stuff. Economies get bigger because more stuff gets brought into economies. And the one I'm most excited about is ecologies. That there's a huge amount of, and what I mean by that is sort of circular economies, all of the things that we currently treat as externalities or as policy problems to solve through regulation or other sort of ways of trying to create governance over problems with industrial spillovers and climate pollution and ecological catastrophes and collapse and so on, just those huge problems that we address. One way to see those problems is that they're problems of computation. We don't know where the excess carbon or the sort of the materials that are being recycled or that are not being recycled out of things. We don't know where they are. We can't see them. That's an information problem. I can't see where you went. I can't compute you. If I can't do that, I can't make rational best use of or efficient use of those things. So this idea of the more we can see, the lower cost it is to interact with all of the things, the better decisions we can make. That's a way of framing what is often presented as a problem of political will, and if we can only just all agree to do the right thing. But it's also just a problem we can't see it. The economy isn't computing all the stuff; it's only computing some of the stuff. And we treat those things as large-scale problems that just seem insolvable and wicked problems, as it were. But a step change in economic computation is one pathway to solving those problems at global scale. Now, that's what I'm optimistic about. That I think some of the biggest problems that we have in the world today, particularly at global scale externalities, of climate, of environment, of biodegradation, and so on, are fundamentally problems of economic computation. We haven't solved them yet. I'm not saying this is a magical solution. I'm saying that the first step in solving them is bringing them into the computation. And so that's why I'm optimistic and hopeful about the prospects that these class of new technologies that enable us to sort of bring things that are outside the economy into the economy so that we can compute them. I think can that's the big step change that this brings.
Yeah, I mean, absolutely. I think you've highlighted there some of the problems that we seem to be systemically just there's some sort of ceiling that we're bumping up against, that this current sort of system substrate we can't seem to compute and solve. And I definitely think there's this huge prospect there that this upgrade will sort of enable us to solve those. I think, that's sort of solving problems, but I think it also unlocks potential solutions. And if you think about, the notion that humanity needs to become a multi-planetary species, for kind of, resilience and survival. It's, that's no longer a science fiction notion. It's, it's one of the core missions of people like Elon Musk. And I think this new upgrade to the economic substrate would much better equip us for doing kind of perhaps multi-lifetime, huge kind of, generational technology builds and creating these kind of new systems to enable us to be, something like a multi-planetary species, which, eventually may be one of the things that determines whether, advanced civilizations survive long term, or not at all. What Robert Hanson would call like a passing through a great filter. So, I think it opens possibilities that we perhaps, can't even sort of glimpse at the moment.
Yeah, very much agree. It's a platform for innovation.
Absolutely. Brilliant. Well, thanks again, Jason. I hope everyone that helped you understand this sort of this kind of thesis that we've been developing. We shall link to the academic paper in the different notes, etc. And thanks for listening. Thank you.